Hello, everybody. It's Dr. Azy. Nice to see you again, so to say. This is going to be the first of our online lectures that is caused by the great COVID outbreak of 2020. So I hope you're going to enjoy this experience we're going to have together. It's very new for me. I'm sure it's very new for you. But if we work at it together, I think we can make this experience just as rewarding as our time together in classes. So I'm obviously recording this in my office on a webcam. You'll be looking at this video. So the way this is going to work is I'm going to just run through all of these PowerPoints with you, just like you were in class. So I want you to approach this just as if you were in class. But the advantage of this is if I'm going too fast, you can pause the video, go back, rewind, have me explain something again. The PowerPoints themselves are all on Blackboard, so you can look at those separately, but you don't have to have those open right now. I'm going to go through them with you slide by slide right now, just as if we were in class together. And so hopefully that'll be an effective learning style for you. If you have any questions, you should just come and see me in my office, virtually, of course, online. So I'll be having the Blackboard Collaborate office hours in a little bit. So the way this is, I think, working is on some of these slides, I don't have any animations, so I'll leave myself open on the right side of the screen here so you can see things. You know, I might be trying to indicate what is a spin doing, tipping, things like that. Sometimes I have to do the animations, so I might have to go to full screen, and then it'll look like this. So you'll just be hearing my voice over the top. And then if I think we can get away with it, I'll come back to this view, and you'll have me here on the right side. So with that said, let's start off with Lecture 25, Magnetic Resonance Imaging. So we have to build on what we had talked about with last time, this idea of the T1 recovery and the T2 recovery, right? The regaining of the spins or the coming back of the longitudinal magnetization and the going away of the transverse magnetization. So we're going to start our lectures, all of these lectures online. I'm going to do them just the way I do the lectures for you guys in class, meaning we're going to start with a question. All right, so I want you to approach these questions just like you did in class. Again, I'm doing this not to assign you guys grades. I'm really doing it because this is going to be the best way to learn. You have to read the material beforehand, right? Try to understand it, get as much as you can, then come to the lecture and go through these multiple choice questions here. Approach them as if this was the exam just to see how much of the material that you got. Give yourself an honest chance to answer the question. So read through the questions and then just hit pause, all right? I'm not going to wait for you, but after you've had a chance to read through them, I'll make sure I tell you, stop the video now, just hit pause, think about it. I would suggest writing down the answers. Actually commit yourself. Don't just say, oh, I think it's one or two. Pretend you're really voting like you were in class, and nobody will know, but write down, oh, I think this is 1 and 3. And then when you're ready, resume the video and then just see if you were actually correct with that or not. That way you're actually committing something to it as opposed to just, oh, I don't care so much. It's just not an effective learning style. All right, so let's start with this then. So the first question for today's lecture, this is lecture 25, is going to be this. So we talked about last time applying the pi by 2 pulse. What is the pi by 2 pulse? Well, if you have a magnetization that's a net magnetization of your protons, that's straight up, the pi by 2 pulse is the spin flip. So the spin flip is going to tip all of those spins into the xy plane. If this is z, then that's xy, okay? And that's the pi by 2 pulse, because pi by 2 is 90 degrees. The magnetization has done that. Now, if you just leave the thing alone, then eventually that magnetization is going to come right back up to where we started, and it's pointing up towards the ceiling in z. But what I'm asking this question is, you hit pi by 2, and if you don't give it a chance to recover, and then you hit it with another pi by 2 pulse right away, what's the effect on the signal? All right, you should have read about this phenomenon in the reading, so go ahead and hit pause now. Okay, if you're back, then you should be ready for the question. And it was number 3. All right, it's definitely not no effect. So because the pi by 2 pulse only acts when the spins are pointing up and it knocks them down 90 degrees, right? If the spins are not aligned with the z-axis, nothing happens, all right? So if you just knock them right away to the xy axis and then you hit it with another pi by 2 pulse right away, nothing happens, all right? You don't knock it back down. It doesn't flip it back up. It's trying to knock them into the xy axis. If they're already there, nothing happens, and that pi by 2 pulse is the start of the experiment. All right, so if nothing happens at the start of the experiment, when you go to make an MRI measurement, it's going to be much, much weaker. And in fact, we're going to use this. This is something called spin saturation. All right, so note I've got the words in pink, right? That's something you should be paying attention to, the idea of spin saturation. We're going to use this effect intentionally later in a very clever way when we want the signal to go away. All right, sometimes we're usually trying to get strong MR signal out of a person, but when you hit it, those spins, we say they're saturated. They've already been tipped into the XY plane. They can't respond to your RF anymore. You have to let them recover first. Hit it again, it saturates, and your signal goes away. All right, that's a tough question. Let's see how you do on the next one. All right, we're going to learn another very important idea in today's lecture, the idea of what's called a spin echo pulse sequence. So the people who work in Dr. Zhao's MR lab, they spend a lot of their time designing brand new pulse sequences. So it's just one of the main ideas of MR. What do we mean by a spin echo pulse sequence? There's two correct answers to this question. What is the purpose of a spin echo pulse sequence? So a spin echo is a very specific type of pulse sequence. You're going to be seeing lots of different pulse sequences. So something that's spin echo or an SE pulse sequence, why do you do it? So I'm not even asking you what it is quite yet, but by the end of this lecture, you need to understand what is a spin echo pulse sequence, but why would you do it? So go ahead and try to answer that. Hit pause now. Okay, welcome back. If you've got your answer recorded, what were the two correct answers to the purpose of applying a spin echo pulse sequence? Yeah, it's two things. We saw in the last lecture that the T2 recovery time is the time that it takes for the transverse magnetization to go away. But T2 star dominates that due to dephasing. All right, so if we're clever, we can apply a spin echo sequence to these spins and allows them to rephase. All right, when you rephase, they come back into phase with each other, your signal returns, and that's going to create an echo that you can then measure. The reason you're doing that is that allows you to actually measure T2. T1 is going to be easier because it's going to be this magnetization coming back. But if you want to know T2, you have to know how they're dephasing with each other just due to the spin-spin lattice interaction. So the point of the spin echo is it allows you to overcome the T2 star dephasing by rephasing them, which then allows you to measure T2. Okay, again, that's a little bit tough. I keep telling you, MR is a complicated idea. So if you haven't gone to that IMEOS website yet, gotten yourself the tutorial, you should really do that now more than ever, because we're not going to be together to talk about these things. You've got to go through them, do the best that you can. Next question. Another third idea. So what have we seen? The idea of saturation, important idea. Pulse sequences and spin echo pulse sequences, that's going to be an important idea. And again, just like in class, we're going to go through all of these in the lecture today, so don't worry about that. But if by the end of this lecture you don't understand these things, then you've got a problem. I would say go back, watch the lecture again, see if you can make some sense of it. So this idea of a T1 weighted pulse sequence, right? So which of the following has to be true? So to understand this question, you have to know what T1 weighted pulse sequence is. Again, if you didn't know the reading, there's no way on earth you're going to know these things. You're not going to know what TR is. You're not going to know what TE is. You're not going to know what T1 is. These are things that you have to know coming out of this reading. So if you know what TR and TE and T1 are, then you know something about them. So in a T1 weighted pulse sequence, which must be true, all right, there are some things that just have to be. So think about this question and go ahead and hit pause now. Okay, welcome back. Hopefully you've had time to think about that. So what was the answer to this one? What did you come up with? Two things were true. All right, in the T1 weighted pulse sequence, we're going to see this TR, which is the recovery time, has got to be greater than the echo time. In fact, that's always true. In all the pulse sequences, not the recovery time, it's the repetition time. The repetition time has to be greater than the echo time. And to measure T1, this is called a T1 weighted pulse sequence because you're trying to make a measurement of T1, and you're going to see that to do that, this repetition time, TR, should be about equal to T1. It's got to be on the order of T1 to probe T1. All right, this is going to be a really, really critical idea, and you have to understand this by the end of the lecture. All right, those are three really tough questions. If you didn't get all of those, that's probably understandable, but it tells you that without math, this is the kind of thing that I am wanting you to be able to answer on exams, right? They're just yes or no questions. Which of these things are true? And they can be really hard. And even though you may have memorized some things, it's going to be hard to get through that way. You have to understand what all these things really mean. Okay, so let's go ahead and start with the introduction, all right? So we saw last time there are 3 times that characterize a magnetic resonance signal. One of them is T2 star, which is the dephasing due to magnetic field inhomogeneities. There's T2, which is the time of the disappearance of the transverse magnetization. That's the spin-spin relaxation. And then there's T1, which is the time that characterizes the recovery of the longitudinal magnetization. So you need to know what T1, T2, and T2 star are to make sense of this. T2 star dominates the time behavior because you're trying to make a measurement, but everything goes away really quickly, and it's due to the magnetic field inhomogeneities. It's not tissue specific, and that's going to be a problem because we want, the whole point of doing this is to eventually to get an image out of the body. And so you have to be getting signal that is dependent on the types of tissue that you're trying to image, and T2 star does not. And that's the only thing that you can actually measure if you're not a little bit clever. So what we're going to try to do is measure T1 and T2, which are very tissue specific, and we're going to use a clever order or sequence of our radio frequency pulses and applied magnetic field gradients. And this is going to be called a pulse sequence. So clearly here in pink, this idea of a pulse sequence, you need to know what a pulse sequence is. By the end of the chapter, you need to be able to tell me what a couple different pulse sequences are, why you're applying things at certain times. All right, so this is a graph that you've basically kind of seen before. All right, so this was the transverse magnetization. We saw that it dephases and goes away, and as this magnetization decreases and sweeps through the RF coil, then the signal that you measure is this free induction signal. All right, so this thing right here, this is your first example of a pulse sequence. It's a very, very, very simple pulse sequence. Let's go ahead and put that up on the full screen for us here, just so you can get a better view of it. All right, this is the simplest pulse sequence you're going to see. All the experiments start with a pi/2 pulse. All right, that's the tipping of the magnetization into the XY plane, which is then going to go away right here. You wait some amount of time that we call TR, right? The repetition time, the time that it takes you to repeat to apply another spin flip pulse, which in this case is another pi/2 pulse. All right. During that time, we have seen what happens to the longitudinal magnetization. Well, it started at 0 when you flipped it down to the XY axis, and then it recovers. And it's going to recover with this with a time characterized by T1. And some long amount of time, like we said 5 T1, then the longitudinal magnetization is back where it started. You can hit it with another pi/2 pulse. It goes back to 0 and then recovers. But the RF signal you measure is being recorded down here. So the radio frequency signal, which is this kind of AC signal here, this is the free induction signal, this is measuring the transverse magnetization. So they call it MX here, but you could just as easily have labeled this as the RF signal. And you can see that you have this quickly oscillating RF signal, and this is characterized by T2 star. All right, and so this sequence is the exact same sequence shown down here. So just like I'm always telling you guys, this is one book's way of showing it. This is another book's way of showing it. So you need to understand what this means, and I need you to understand what this means. So we're applying a pi/2 pulse. So here they call it 90 degrees. Here they call it pi/2. Same thing. Here they're showing a free induction signal decaying as T2 star. Here's the free induction signal, FID, decaying as T2 star. All right, this is due to the dephasing of those spins. What we would like is that signal should be going away as T2. This is the time that we want. We're trying to measure that. But it goes away much, much quicker due to T2 star. And just to remind yourself of what this dephasing looks like, you can go back and watch that Principles of MRI right here. All right, here was the video. Let's bring this guy up. And right, this is the dephasing in the XY axis. Remember, there's a net magnetization vector, but it goes away because all the spins get out of phase with each other. That takes some amount of time, but when that is caused by the magnetic field inhomogeneities, that's the T2 star time, and it goes away really, really fast. All right, and when it goes away fast like that, then you cannot measure the dephasing caused by the different tissues, which is what we want. So we've got a problem. All right, it's a big problem. So this is a very, very simple pulse sequence with a pi/2 pulse, and you do nothing, and you just measure the free induction signal that comes after it. Okay. So now, here's the trick. That dephasing is the killer. T2 star makes your signal dephase, but not on the right time frame. So how are we going to do it? So we are actually going to intentionally rephase it and watch it. We're going to do that repeatedly, and then the dephasing that occurs is going to be due just to T2 star. All right, so this slide is called the spin echo. This is going to be our trick for reversing or undoing that dephasing. All right, so it's going to be really, really important. So let's see how that works. So let's remind ourselves of what's going on here. So I showed this video in class before. This is the top-down view of the net magnetization. It's in X and Y. It's going to be spinning, right? And it's going to go away. Yes, now it's a little shorter yet. You can see that all the spins are getting out of phase with each other, so the vector sum of them is getting shorter. It's getting shorter. It's getting shorter, and eventually this is going to go away. This is all due to T2 star. All right, now we're at essentially nothing. All right, so we saw that video before. That's the dephasing due to T2 star. So how are we going to get around that? Well, we're going to do something really, really, really clever. All right, we are going to get a rephasing using something called the 180 degree or pi pulse. So the pi by 2 pulse flips the magnetization from Z down into the XY plane. The pi pulse or 180 degree pulse is what we're going to use to get these guys back in phase. Watch this animation and then I'll come back. All right, that's pretty cool, right? So I'm going to play it again, but pay attention to what happened. So these things were rotating in the XY plane. The pi pulse is going to flip them around the x-axis, and then they're going to continue their journey. But the result of that is going to be that the spins that we're getting out in front are now going to be at the back. The spins were at the back, we're now at the front, and when they come back around, they're back together again. Let's see if I can pause it and show you what I'm talking about. Okay, pause it here. Do you see this spin is maybe going a little faster? This spin's going a little slower. He's at the front, he's at the back. Now look what happens when you flip them around the x-axis. Boom. This guy that was at the front, now at the back. This guy was at the back, now he's at the front. He's moving more slowly, he's moving more quickly. When they come back around, the one behind catches up, boom, right back into phase. Okay, so bringing them back into phase makes your signal reappear. All right, so that's what we call, with the pi pulse, we cause an echo, right? The magnetization was going away due to T2 star. You hit it with a pi pulse, you wait some amount of time, and they come back into phase, and your free induction signal, which was going away, comes back. It's an echo of the original pulse, and that echo is strong enough to be measured. All right, we like to use an analogy of that. So let me just take you through. I'm going to put you on full screen here so you can think about what this is showing. All right, perfect analogy. Imagine 3 runners on a track, runner red, green, and blue. They all start at the starting line of a round track, and they're going to do a race running around the track. They all start together. They're in phase, right? They're at the starting line. That means they're together. That means they're in phase. How do you start a race? You start a race with the firing of a starting gun. Bang! What's the starting gun in an MR experiment? It's the pi by 2 pulse. It's the 90 degree pulse. That's always what starts your experiment. So they start in phase. You apply the pi by 2 pulse. That's going to rotate everything into the XY plane like this, and then they start going. Now, just like 3 runners on a track, you don't run at the same speed, right? So let's say that green is the fastest. So that green gets out ahead. Red is the slowest. Red gets furthest behind. So I'm showing runners green, blue, and red. And where is their position on the track? Green ahead, red behind, blue in the middle. Here they were in phase. Here they're getting out of phase. This is the analogy of the spins getting out of phase due to the T2 star dephasing. All right. So what do? We let them run for a while, but what if, unlike in a regular race, you let them complete all the race. What if they got about halfway around and the referee or the track umpire suddenly blew a whistle and everybody had to stop, and they stopped right in their tracks? Red was furthest behind, green was furthest out ahead, blue was in the middle. All right, the equivalent of the referee blowing a whistle is the 180-degree pulse, or the pi pulse. All right, that stops everything, and it makes them go now backwards. So the referee or the track umpire doesn't just blow a whistle to make them stop, but everyone turns around and goes back the way they came. Now, red, who is slowest, is now out in front of everybody because he's got the shortest distance to go to get back. Green was way out in front, but he's now got the furthest distance to go to get all the way back around. Importantly, the time we apply this, the pi pulse, occurs at a time called TE over 2, right? The echo time divided by 2. Why is it TE over 2? Because if you wait the exact same amount of time it took TE over 2 to get here, it'll take exactly TE over 2 to get back to where they started. So at a total time TE, after the application of the pi by 2 pulse, so this is time 0, this is time TE over 2, this is time TE. At that time, all the runners are back to the finish line at exactly the same time, and they will finish that race in a tie. The MR equivalent to that is all the spins are back in phase, your MR signal returns from 0, and you now get a spin echo. All right, so hopefully that analogy makes some kind of sense with you. So again, I don't quite know exactly what mental picture you have to have in your mind. I think this picture of the runners on the track is not at all a bad example, but you saw the animation of the spins flipping around. Just remember the things that were behind catch up to the things that were ahead only after you apply the pi by 2 pulse, or the pi pulse, I'm sorry. So what have we learned so far in this lecture? Pi by 2 pulse rotates to the XY plane. Before they have a chance to recover, they get out of phase in the XY plane. You apply a pi pulse, which causes a rephasing, which will then allow us to measure the T2 recovery time. So what's the idea of that? This is going to be called a spin echo sequence. So you note I'm modifying this spin pulse sequence that we had before. Before we had the pi by 2 pulse and it just recovered, and then the pi by 2 pulse, and that was it. Now let's see what happens on this pulse. All right, so the pi by 2 pulse comes, and here I'm showing this graph is from one book over here, this graph from another book over here. They are showing exactly the same thing. So on a pulse sequence, what you're always showing is the RF pulses coming in. So here it says pulse, pi by 2 and pi. Here it says RF, 90 degrees, 180 degrees. It means exactly the same thing. You guys need to understand both of these pictures. Here it's showing MX, which is the X or transverse magnetization. Here it shows signal. This is what you measure. All right, so a spin pulse sequence always has the RF pulses you put in. It's always got the RF signal you measure, and then there's going to be some magnetic field gradients in between. We're going to add those in the next lecture. But now look, you applied the pi by 2 pulse. So the magnetization in the longitudinal direction went to 0. It starts to recover, and then you hit it with the pi pulse. The pi pulse comes at a time TE over 2 after that pi by 2 pulse. You wait another time TE over 2 for a total time of TE, and that's when your echo comes back in. If you do this a few times in a row, then you just plot the decay of this echo to this echo, to this echo, to this echo. It'll get smaller and smaller, but it's going to get smaller along this curve, which is decaying according to T2. So with 2, 3, or 4 of these measurements in a row, you can quickly recover the T2 time. Eventually, though, you can't undo all the dephasing. It's going to go to 0. That's fine. Start over with another pi by 2 pulse, which restarts your experiment, and then you do this whole thing over again. Okay, so hopefully that makes some kind of sense. So let's take a look. This is a spin echo sequence. The spin echo is there to measure T2. So we have this word called weighting. What does weighting mean? Weighting means you're going to be adjusting where the pulse sequences are being applied in order to measure a specific thing. So T2 weighting means it's a pulse sequence designed to allow you to measure T2. And that's what we're going to be trying to do. All right. So this is just a particular type of spin echo sequence. A sequence of sequential pi pulses make this what's called a car per cell sequence. So this is definitely a car per cell sequence. So look what happens. Here's in green. I've tried to make this nice and easy to see. These are your 90-degree pi by 2 pulses. Start of experiment, start of experiment. At a time TE/2, you apply this 180-degree or pi pulse. And then at another time TE/2, the echo comes back. You wait another time TE/2, apply another pi pulse. Wait another time TE/2, and here comes another echo. But now this echo here is smaller than this echo here. And you're going to measure this decline. And you wait another time TE/2, apply a third pi pulse. You wait a time TE/2, here comes this echo again, smaller yet. Do this, get another echo, smaller yet. Each of these echoes is going to be smaller, and what that'll allow you to do is measure this curve. Like I said, you need about 3 or 4 of these measurements, and then you'll know exactly what T2 is. All right, T2 star is this going away. T2 is this going away. And then eventually this echo is going to get so small you can't do any more. It's fine. Time to start a new experiment. Hit it with another pi by 2 pulse. Wash, rinse, repeat. And you can do this as many times as you want. So think about that. Make it make some sense. Pause it now if you want to rewatch these things. Really try to understand. Combine this with what Kane and Hobby were trying to tell you. All right. So let's just get some numbers down. So TE is the echo time, right? So it is the time, since this is TE/2 and that's TE/2. TE/2 plus TE/2 is time TE. That's the echo time. So it is the time between successive pi pulses. All right, this is TR. It's the repetition time, the time between successive pi by 2 pulses. So now you can see in that multiple choice question which started the lecture why TR has to be bigger than TE. All right, you can see this from this picture. There's no way that TR can be less than TE. Usually there are multiple echo times within every repetition time, like that. All right, that has to be true. So these things are both set by you. That's the cool thing. T1 and T2 and T2 star are set by the magnet and the tissues. There's nothing you can do about that. TR is determined by you as an MR operator, as is TE. These are your user modifiable parameters. You choose them to be whatever you want to make the image look like whatever you want. This is really one of the keys to MR. You choose TE, the echo time. You do it so that each time you apply the pi pulse, the signal is measurably different. So we want TE to be about equal to T2, right? Remember this. This is really important. Don't just memorize what they do. TE is chosen to allow you to measure this T2 decay. So if TE is super, super short, then every time you measure these echoes, they haven't changed at all. It would be like blip, 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 blip. What does that get you? Nothing. On the other hand, if TE is really, 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 really long, you'll get one measurement, and then by the next time you measure, it's down to 0. And what does that get you? Nothing. TE needs to be on the order of T2 such that between each successive echo, it's actually changed by a reasonable amount. It allows you to measure the change in signal depending on T2. All right, so I need you to know that to make a T2 measurement, TE is about equal to T2, but also why that's true. All right, don't just try to memorize these things. I've seen so many students, and it will bite you on the exam, that if you just try to memorize what these things are, it just doesn't help you. All right, you're not going to be able to keep it straight in your head to be able to answer the questions I want to know. So you really need to think about this. All right, so this is what I was just saying. There's a caveat. If TE is too short, you won't see any difference at all. It's insensitive to T2, right? Imagine you just apply a bunch of pi pulses right away. It doesn't have a chance to decline at all. You can get 5 in a row, and this echo-free induction signal has not changed. You can't measure anything. And if TE is too long, obviously, you can't wait forever because the signal does go away. All right, it goes away on the order. By the time you've waited 3, 4, 5 times T2, the signal's gone. So you can't wait that long. So it has to be right on the order of T2, not too short, not too long. All right, I hope that makes some sense to you guys. Well, if there's a thing called T2 weighting, which you need to measure the T2 recovery or relaxation time, then there must be a thing called T1 weighting, and we're going to see that that is true in a minute. So for people who are worried that there's no equations to this, sure there are. Here's the equation. I know this looks scary, but it's not all that scary. We're going to see there's three parts to it. There's a term here that's the density of the protons. There's a term in square brackets, which is just going to depend on T1 only. And there's this term hanging at the end, which depends on T2 only. So it's really only 1, 2, 3 terms to this. And you'll know what each one of these 3 terms does in a bit. This is capital S. It's the signal, the MR signal as a function of time. So it depends on TR, which you choose, T1, which comes from the tissue, TE, which you choose, T2, which comes from the tissue. This is what allows you to make the measurement. All right, you're going to pick TR and you're going to pick TE in such a way that the signal reflects either T1 or T2. So let's talk about this T1 weighting. All right, so here's the same kind of graph. And I'm going to start off the question with T1 weighting by asking you a question. And again, when I'm done asking the question, I want you to pause the video and really think about it. You know, don't just blow through these things, although I'm sure you're all enjoying your time at home and you want to get back to doing whatever you're doing. But we've got to try to learn this. I mean, I need to hold you responsible for these things. So take a look at this. I've shown the same graph before. In this particular picture, pi by 2 pulse, and then a sequence of pi pulses, which makes this a spin echo car per cell sequence. TE is the echo time. It's the time between these red pi pulses, or it's also the time between the echoes. So that, and if I ask you what is TE time, it is both, because that time is exactly the same. It's the time between successive pi pulses. It's the time between successive echoes, because they're both TE over 2 plus T over 2. And here's the repetition time. Now, when I talk about T1 weighting, I'm only talking about TR. So in this particular figure, is T1 the time set by the tissue, is it greater than TR, the repetition time, or is TR less than T1? How can you tell just from this picture? And it's important because I need you to be able to do that. So go ahead and pause the video now. Okay, so you've come back and you're trying to figure out, oh my gosh, from this question, how can I figure out if T1 is greater than TR or TR is greater than T1? How can you tell? Well, here's the thing. If T1 is much, much less than the repetition time, meaning that it's recovering much, much faster, when the next pi by 2 pulse comes in, which is going to be this green pulse right here, or what was green, right here, the spin situation is identical and the echo intensities are the same. So look at this pink line that I've drawn. I'm sure you weren't paying attention to this before. All right. If you wait long enough with your repetition time, so you wait a long, long time, all these spins have relaxed fully. There is no saturation. And when you apply your next 90-degree or pi by 2 pulse, everything is identical to what it was at the beginning. And this echo right here, this first echo, will be just as big, that is here, as it was at the beginning. And then you know that T1 must have been shorter than TR. What if that wasn't true? So I'll ask you the other question. In this case, so I show you this picture, is T1 greater than TR? Or is TR greater than T1? How can you tell? Well, you just look. These pictures look the same, but they're not. Because look at the first echo after the pi by 2 pulse. It's here. Look at its intensity. It's way weaker than it was at the first one. All right. Here's what it was after the second pi by 2 pulse. Here's what it was after the first pi by 2 pulse. In this case, T1 was probably longer or greater than the repetition time, because when the next pi by 2 pulse came along, the spins yet have not had a chance to realign along Z. So we say that this is a situation of saturation, or it's partially saturated. When they're saturated, they do not interact with the RF field well. And when that happens, the intensity of those echoes has to be lower. All right. So this is the point. We're talking about T1 weighting. You can choose the repetition time such that each time you apply by 2 pulse, the signal is just a little bit different. we want TR about equal to T1. The change in the signal will depend on your T1, and that allows your measurement. In the same way, if TR is way too short, you have a very short repetition time, MC will not have recovered, there won't be any signal left. This was called full saturation. If the TR is too long, you don't see any difference at all, and then you're not actually measuring T1. You need a TR time that's about equal to T1. So let's just go back and look at that T2 and T1 weighting again. Let me just summarize real quickly, all right? Because this is the key. If you want to measure T2, then you pick an echo time right here. The time between pi pulses about equal to T2. You do it a bunch of times, bang, 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 bang. If TE is about equal to T2, then every time this echo comes back, it's changed a little bit. You get 3 or 4 of those, you can measure that pretty darn easily. But TE can't be too short, or you won't see any difference. TE can't be too long, or the signal will have gone away. In the same way, right, in this T1 weighting, which I'm showing here, if it's T1 weighting, we choose TR now. And you want TR to be about equal to T1, such that when you come in after another time TR, this thing has changed a little bit. But if you wait a very short TR time, then none of the spins have recovered, and you'll get no measurement. You'll just get no signal. If you wait a long, 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 long time, then when the spins are fully recovered or fully relaxed, and when you do the experiment, it'll be exactly the same and you won't have seen any difference at all. So once again, you have to choose TR right in the Goldilocks spot, in the sweet spot, somewhere equal to T1 such that there is a measurable change. And again, this equation is going to kind of control that. So let's just sum all this up here, all right? So I want to show you this slide here. So here is this master equation, all right? So we've got the signal that you measure, and you have a choice. And this is where all the students in this class really, really, really get confused. On the other hand, always about 50% of the students can answer these questions perfectly, which you're almost certainly going to see on an exam, on the final or the midterm, which is how do you adjust TR and TE, which are the things you can adjust, right, to get a one of these different weightings. So there are 3 terms here that I've shown. This is rho. It's the density of protons. So if you don't want to, there's the third weighting. It's called proton density weighting. There's only 3 weightings, and I'm showing them on the left of the screen here. Proton density weighted. I don't want to measure T1. I don't want to measure T2. I just want to know how many protons are there. And that's useful because like fluids have different numbers of protons than gray matter, than white matter, than muscle, than lung tissue. So that can be useful all in and of itself. That term's going to be dominated by this rho, the density in X and Y. So if I want this term to give me a measurement, I need this term to be 1, and I need this term to be 1. So it's 1 times the density. So if I want this term to be 1, I need TR to be much bigger than T1, which makes this e to the negative something big, which is 0. 1 minus 0 is 1. This term, I need TE to be much less than T2, because when T is much less than T2, I have e to the negative 0, which is essentially 1. All right, so proton density times 1 times 1. It's only dependent on proton density. That's called proton density weighted. So this is a long TR and a short TE is called a proton density weighted sequence for this reason. What if I want T1 to dominate? I need this term right here to dominate. Want this term to dominate. What do? Well, I need TE to be much less than T2 in the same way. That way this term is always 1, right? E to the negative something small close to 0 is essentially 1. This term now is not 1 or 0. It actually is something measurable. I need TR on the order of T1. So this thing is not 0 or 1. It's something in between. It allows me to measure it. Now the proton density is always there. That's true. But this is the term that's actually dominating. You're doing an experiment which allows you to measure that quantity, and then it's superimposed on top of the proton density. So if you have a short TR, short means it's on the order of T1, and a short TE, which means it's much less than T2, we call that T1 weighted. The last type of weighting is called T2 weighting. I want a type of a map of the tissue which depends only on T2. If that's true, then I need now this term to be 1. So if I want this term to be 1, how do I do that? Just look again here. If TR is much greater than T1, you have e to the negative big, which is 0, and then 1 minus 0 is just 1. And then this term will carry all the weight. I want TE to be about equal to T2. So this term is not 1, it's not 0, it's something in between. It allows you to make the measurement. And that's called the T2 weighting. So I do need you, coming out of this lecture, to know what a proton density weighted sequence is. I need you to know what a T1 weighted sequence is. And I need you to know what a T2 weighted sequence is. I need you to know what TR is and what TE is. And I need you to know how you pick TR and TE to get those different sequences. I would suggest strongly you take this is the math behind why that happens. These are the actual numbers that you use. This is a very easy kind of graph to look at. Here is the exact same things to sum up that I've got up here. I've got them right here. All right, but this is a very convenient graph where I'm plotting TR time, repetition time, versus echo time right here. And you can see that the TRs are, these are actual clinical times. They're quite bigger, 500 to 2500 milliseconds. And this is all under 100 milliseconds right here, 20 to 90. So just look, if I want this proton density weighted, I need a long TR and a short TE. That's out here on this edge of the graph where it's black. Long TR, very short TE is down in this corner. On the other hand, if I want T2 weighted, I want long TR, but long TE. That moves you up to this area up here. And if you're down in this corner, then I have short TR, a short TE, and that'll be a T1 weighting. And I just explained why these things are before. So short T1 means TR is about equal to T1. This probes your T1 relaxation. TE is shorter than T2, so there's no T2 relaxation. So it's just 1. And then each of these are the reasons for why that is. I would encourage you to look at this graph carefully. If you don't understand it, try to work through it. If that doesn't make any sense, then talk to me in the office hours and see if you can make some sense with that graph. That's going to be kind of important. Here's another way of presenting that graph. So again, I'm just summing up all this stuff again right here. So these are the same things, long TR, short TE, short TE, short TR, short TE. You can try to memorize those. I don't, because I think I would get confused, but I can always figure it out if I just remember how this equation works. If you think that's going to take too long, at the very least, you're going to have to know these things. All right. And here I have just, you might be wondering, what does he mean by short and long and stuff like that? Well, short TR, clinically, value equal to the average T1. So that's going to be smaller than 500. Long TR, usually about 3. When I say long, it's about 3 times that. So long TE means 3 times whatever the shortest TE is. So greater than 90 milliseconds, something like that. All right. So if TE is about 20 to 30 milliseconds is the shortest one, 3 times that, about 90. Short TE would be shorter than any of the shortest ones, so lower than 30. Right. So that tells you that, this is a second and a half, 1500 milliseconds. These are quite fast. So you can do a lot of these in just a few seconds. All right, let's just take a look at this. So you take a look at this. Now, I don't expect you to know this right now, but this is the kind of thing that you need to be able to answer. So for the following 5 tissue types in a T1 weighted image, which tissue is darkest and which is brightest and why? So I know this question doesn't make a lot of sense right now, and if I asked you, you probably wouldn't be able to get it, but this is the kind of thing that I think we would be doing together in class. And I would probably ask you that question. I'd have you discuss it in teams, but maybe think about it now. All right, so it's a T1 weighted image. Which tissue is darkest? Which is brightest? Why? Let's talk about that. Well, in a T1 weighted image, water, which has the longest T1 time, is dark. Fat, which has the shortest T1 time, is bright. Why? All right, well, remember, you choose the repetition time. All right, so you choose the repetition time. Go back to your equation. This is the term that controls T1 weighting. So if TR is really, 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 really long, and it's going to be on the order of, 3 seconds for water, something like that. So this is a T1 weighted image. That means you're setting T1 to be about equal to TR. So this term should actually be something like 1 minus 1 in that case. So it starts to get dark and your signal will be very, very small. In the T1 weighted image, T1 is about equal to those TRs, but one of them, the TR you've chosen there, T1 is quite small. So when T1 is small, like it is for fat, whatever you've chosen for TR, you're dividing it by the small number. So that's e to the negative big thing. 1 minus e to the negative big thing is close to 1. That's going to be bright. Right? When T1 is very large, like it is for water, no matter what you chose for TR, T1 is big. So something divided by something big is something very small. E to the negative small is essentially e to the 0, which is 1. This number is like 1 minus 1. It becomes 0 overall, so that thing is dark. All right, I know that's hard to understand, but really try to think about that. In a T1 weighted image, when T1 is long, it has to be dark. And when T1 is short, it has to be bright. And that's why, because the things have not had a chance to recover yet. So anything that takes a T1 is long, it just means, let's take a look at this. So T1 is the recovery in this plane. So for water, it takes a long time for it to come back, right? It's more like the longitudinal relaxation is slowly coming back. So for water, it takes forever. And you're choosing the repetition time such that no matter where it is, bang, the repetition time is bang, bang again. If it hasn't recovered, when you do bang, there's nothing to recover. It's black. There is no signal, right? Look at fat, though. Fat has the very short T1 time. So very quickly, whoop, longitudinal magnetization comes back. Your TR is the time for bang. Oh, nice strong echo. It comes back. Nice strong echo. Bright. So if it's fast recovery, your TR time is how long do you wait for the another pi by 2 pulse? It's all ready to go. The shorter it is, it's ready, flips back over, it comes back, no problem. Nice bright signal. The water is real slow. This is this idea of saturation, spin saturation. It's trying to recover longitudinally. It hasn't recovered yet. You hit it with another pi by 2 pulse. It's like, ah, crud, I'm not ready to go yet. It just can't recover. There's no signal. It's very dark. All right, you have not let it relax that way. On the other hand, my next question here is for the following 5 tissue types, these 5, in a T2 weighted image, which tissue is brightest? Why? Now, what's important to remember is it's not, oh, brightest in T1 is brightest in T2. In general, that's not true. So if your first thought is, oh, well, it's bright in T1, fat, so I'm going to say fat again, probably your first thought should be, no, let me just pick the opposite. That's not always true, but T1 and T2 are not the same thing. So if it's brightest here, it's probably not going to be brightest in T2. And in fact, yeah, it's just the opposite now. In the T2 weighted image, now what was darkest in T1 is brightest in water, is brightest in T2, and that's water. Why is that? All right. Well, to answer this question in the T2 weighted image, forget these numbers. If you're talking T2 weighted image, it only depends on T2 and TE. So in a T1 weighted image, you look at T1 and then think, how did I choose my TR? In a T2 weighted image, you look at T2 and you say, how did I choose T2? So in a T2 weighted image, which tissue is brightest? Water. Water has the longest T2 time. Well, what does that mean? Well, let's take a look. Go back to our master equation. Here it is. Again, forget this term right here, because remember, in the T2 weighted image, you want this term to be 1. So you've just picked TR such that whatever it is, all this stuff is 1. All the action is right here. And you ask yourself, is this term 0, which means dark, or is it 1, which means bright? Just ask yourself that. And you need to know this much math, which is not unreasonable to know. So you've chosen TE, whatever TE is. T2 for water, it was the biggest. So E to the negative something over something big Whatever TE is, the denominator is huge. That means that this number is small. It's essentially 0. E to the 0 is 1. So something with a big T2 makes this whole term 1, which means it's bright. What happens if T2 is very, very, very short? Then it doesn't matter what TE is. Something divided by something small is a big number. E to the negative 3, e to the negative 4 is very close to 0. And that means it's dark right there. So again, how are you going to remember this? Think about my chart. Make it make some intuitive sense to you. Think about those pulse sequences. Think about this equation. You can always figure this out. Think about the examples we're going to see. There's no one thing that'll make it click for you. And again, I'm sorry, I know I've told you guys this before. It's complicated. All right? MR is the most complicated thing we're going to talk about. This can be confusing, but on the other hand, plenty of my students are able to do this every year. So you can too. You really can. You just got to struggle with it a little bit. Do those animations. All right? See if this makes sense. You do have to know what e to the negative something does. If you don't know that, well, it's the end of a second year physics class. You need to know that, right? E to the 0 is 1. E to the negative 1,000 is essentially 0. And what are things in between? So just look at these fractions. E to the negative of that business, what does that give you? And then what does that thing tell you to do? Conversely, it does not hurt to just be very familiar with these charts and just, kind of understand what they are. So memorizing wouldn't hurt, but then also understanding why they are what they are. So I can ask you questions. Why would you want T2 to be about this? And your answer is, because here T2, it's about TE. I want to probe those T2 times. What's the purpose of them, right? Because I like to ask questions. Why would you want T2 to be about equal to TE in a T2 weighted thing or something like that, all right? So if you have any questions on this, you've got to come talk to me. Now, let's just take the last couple minutes to talk about why that is. Because now look at this question. In a T1 weighted image, water is dark. But in a T2 weighted image, water is bright. This is the power of MR. Look at these 3 images. All right. This is the idea of weighting. So we're looking at what is the effect of MS, multiple sclerosis lesion, in the brain. So we've got 3 different weightings. So here we have, these are all MRs, but just by controlling the experiment, you can make them look different. All right, so this is a T2 weighted image. This lesion here, due to the MS, is quite bright. Here is another T2 weighted. This is a different type of T2. It's called flare, so it's a little different. But here's a T1 weighted. So let's just look at the T2 weighting and the T1 weighted. And it's all about contrast. Would you say that you can see these lesions better here or here? Well, the point is you can run the experiment and set the contrast where you want it to really visualize what you're doing. That's something you cannot do with CT. All right, so in general, here's another useful graph. You can just look at these things. A tissue with a short T1 along T2, like fat, is bright in T1 weighted image and gray in the T2 weighted image. A tissue with long T1 and T2, like water, is dark in T1 and bright in T2. So these are just things that are useful to know. In general, T1 weightings will produce high intensity signals, that means bright, for fat and bone marrow, and low intensity signals, which means dark, of muscles, water, and collagen. That's just generally true, and it's all set by the TE time. All right, so this is the idea of weighting. So this is the exact same brain slice into which you've done T1 weighting because you're measuring T1 relaxation. You've done T2 weighting because you're doing T2 relaxation. And here's just the proton density weighting. Now these things look the same, okay? But there are certainly different contrasts between these 2 images. Now which one you want, that's up to the physician, right? They're looking for different things. We're not physicians, so it's okay that you don't know which settings you would choose. But like I said, in an actual scan, they're going to run a bunch of different weightings when you're in the machine, and then they will look at the ones which give them the information that they want. Right, so here's that same kind of graph again, just showing different slices of the brain. Here's kind of a cool slice. So look at this. So here is the spinal column, right? So anybody who's interested in visualizing spinal cord, cervical injuries, things like this, back problems, MR is the preferred mechanism for that. So on view A here, we've got a sagittal, which means sideways view of the body, T2 weighted image. So this is a marked, this is C5, so it's the cervical vertebrae, C5, C6 cord compression. All right, so this would be very, very worrying to a neurologist because this person's going to have mobility issues because their spinal column is being compressed. But which is easier to see? Can you see that damage in the T2 weighted image? Same patient, same experiment, but now you're doing a T1 weighting. Not so easy to see. But here they are showing moderate spinal cord enlargement right here below the C5, C6 level. All right, so certain contrast mechanisms show different types of information. So this is the reason why you would do it. Again, T1 weighted with gadolinium, we'll see what that is in a bit. T2 weighted of the brain, exact same slice of the brain, you just done a different experiment. Here you can see a lot different detail in the ventricles than you do over here. On the other hand, the difference between the gray and the white matter might be more pronounced here than it is here. So in practice, you would acquire all of these images, right, and do something with it. And here's just an interesting one, which is a lesion in the person's spine due to parasitic infection, right? So here you can see a lot of really interesting detail of this infection, and here not so much, all right? This is the exact same patient. You just run different types of experiments. So it's really useful to know which of those is going to be most useful. Okay, so that's a lot to chew on. Again, not a great time of the semester for us to have to be apart, I will admit, because MR is the most complicated subject. But like I said, at the very least, you can go through this as slow as you want, go back, rewind things. Maybe you can have my PowerPoint slides. They're already posted. You can watch those and go through them yourself anytime you want. But here's me kind of narrating what these things are. Jot some questions down to yourself. Let's talk at my office hours whenever we can. I don't think sending me emails is a good way to do it. It just takes too long for me to type and explain things. When you come to my office hours, we should be able to video conference this way. We'll be looking at each other through the Blackboard Collaborate site, assuming it works. And that's what we're planning to do. So this is the first of the video. We've got 6 more lectures coming up. I am going to ask MR questions on the midterm, which is coming up. So please do try to understand this the best you can. Be working through your homeworks all right now. Get ahead of this material. Don't get behind. Don't get confused. Get help when you can. And I'm going to try to help you guys get through this. So hopefully this is the first video was kind of successful for you. We'll see what happens. They're all going to be like this. I'll probably stick with this modality of doing it because you can see my PowerPoints. You can see me, not just a floating voice in the ether. And then you can show the animations on YouTube that I've been showing. If you have any feedback on these videos going forward, please let me know. Unfortunately, I'm probably going to record at least the first 3 of them right away. So if there's something that's really annoying, I won't be able to fix it right away. But as soon as you see something that you think I could easily do better, let me know and I can make that change. Hopefully the last videos maybe will be a little more to your liking. So good luck with that, and I hope to talk to you all soon. Good luck.